Hello, good morning, good afternoon, good evening, everyone. Please let us know if you can hear us and see us well. We are starting soon. We are starting in about 3-4 minutes. So let us know. I see already that we have Bridges by Martin. Hi, Martin. Good to see you here. We have also Omar with us. Just leave a comment if you can hear and see us well. So soon we will start. So we have already our guest. So I would like to welcome Matthew Tam. Hi, Matthew.
Hi, Chris. Thanks for having me. And
Yeah,
excited to share Karamba3D with everyone today.
yeah. We will start exactly at 2 p.m. So yeah, so let's prepare for that. We have Luis, we have Xavier, so it looks like everything is working right now. Let me see. I will check. Hi, Marek. You are with us. Um, good to see you here. Okay, so let me see. I will share my screen right now. So let's present it. Just let us know if you have used Karamba from before. Maybe you're already Karamba user, or maybe you heard it for the first time. So just let us know in the comments if you have used Karamba before, if you know this software, this plugin to Grasshopper. So let's use. Do we have some users here? We have Jason. Hi, Jason. Yes, we have some Jason Karamba user. Good to see. Good to see you. So we have Joshua as well, who's using Karamba. Yeah, lots of Karamba users. So
That's good
good
to
to see.
see.
Maybe Matthew, you already know some names. Maybe Luis Felipe. Maybe
I
already you
think
know from that some from
yeah,
tasks.
yeah. I think some people I recognize the names, but yeah, it's nice to see you all here. I think it's a great community.
Yeah, it's already. I see that it's already growing. When Karamba started, do you know? Like, what was the first like?
We started just over 10 years ago. I think last year we crossed the 10-year mark. So
Mhm.
yeah, it's been up and running since 10 years and developed quite a lot in the last 10 years, I would say. And yeah, so we've been pushing a lot in the couple of years, especially. But and hopefully,
When you have started, or
oh,
from the beginning, from the scratch, have you started from the beginning, from the
no,
scratch?
I think I've been with Chroma around 7 years. Yeah,
Okay.
so close to the start, but one
Mhm.
of the first to join Clemens in the team. Yeah,
Yeah. Yeah,
but
I had the pleasure. I had the pleasure to meet Clemens on the last Rhino meeting.
yeah,
So he's the founder, right? He's the CEO who started.
he's the founder and the starter, and I think that's also where you kickstarted this whole initiative, right? To
Hmm.
invite us to have one of these webinars, and
Correct.
hopefully a course in the future. We'll see.
Yeah, we'll see. We'll see
Yeah.
about the interest. So today we'll see if there will be some people interested in Karamba and maybe making course together. So we'll see. Yeah, we have Luis Xavier. I have looked into it, haven't actually used yet. So good to see you here because Matthew is going to present some really nice use cases. So I'm really looking forward to this one. Okay, it's already 2 p.m. So let's start it. We have already some people on YouTube and LinkedIn, so we are live. And as always, if you can just leave a like on the if you are watching that on YouTube or LinkedIn or Facebook, so it will be great. So a little bit information today. Session time. Will be about 40 minutes. About 40 minutes of the content. Then we will have a Q&A session. It's about 20 minutes, but of course, if you will have some questions, so let's put it on the chat. I agree. I agreed with Matthew that we are going to try to answer all of your
Mm.
questions. but still, maybe not. We are not going to solve all of the issues that you're having. So maybe if you have some technical issues, so maybe it will be redirect you afterwards to support. But yeah, but if you have any question about Karamba and maybe some new features, so just leave a comment. I already saw the question if there will be recording available. Yes, everything is recorded and it will be placed on the platform, and you will get the recording after registration. So if you register on learngrasshopper.com/webinar Karamba, so you will get recording after this session is finished. And Matthew prepared also Grasshopper files. So this is a really cool thing. I already seen these Grasshopper files. So there is lots of stuff in that one. So Matthew is going to present the most of these Grasshopper files, and he already shared with me. And if you registered your email on the learngrasshopper.com/webinar Karamba, so you will get all these Grasshopper files. So it's really worth to register. And as I said before, if you have any questions to me or Matthew, so write in the comments below. So benefits from joining this webinar, what we are going to talk about Karamba and its application for the structure analysis, how we can calculate and analyze the structures, how we can also optimize the structures with Karamba. So Matthew is going to show real project examples. I'm really looking forward to this one. I saw some of them and they are really gorgeous. And of course, we have the interactive session. So I encourage you to ask questions because this is a chance to actually get the first news from Matthew about the new releases. When was the newest release of new Karamba?
We have a beta release already, but we're hoping to officially release the next version in hopefully a couple of weeks, maybe a month or so.
Yeah.
We'll see how things go.
So maybe Matthew can reveal some of the secrets which are coming to you in the newest version of Karamba. Okay, so we are starting right now. We are not going to wait anymore. So I present first of all a little bit myself. My name is Krzysztof Wojsław. I'm a founder of learngrasshopper.com platform when I'm trying to teach engineers how to start with computational design, how to start programming in the AEC industry. I try to share my knowledge on LinkedIn, but I'm also on the working as an academic lecturer on the Norwegian University and Ziggurat. But this meeting is not about me. Together we have Matthew Tam. He is a computational designer. He worked in Karamba and as a computational design in the Bowling Graham. Is it correct?
Bollinger Grumman, yeah.
Grumman, yeah.
Nearly.
Yeah. So so you said already before start that you started in Karamba 7 years ago, right?
Approximately 7, yeah.
But are you working there 100% or?
No, so I'm part-time at Karamba3D and also part-time at Bollinger Grumman. So we split. Also, me and Clemens, we're both working at both offices too. So we also use the developments in the office in sort of everyday practice to really test out the features. Yeah.
Yeah. So in Bollinger Grumman, you are also working with Karamba, right? Or are you using another software?
I mean, we're using Karamba3D as the main software, but of course, there's other softwares that we also use in our package. Yeah.
Yeah, but it looks like a great combo if you are developing on the one side and you are also working a little bit with the projects because you are both working on some projects, right?
Yes, yeah, we're both working on projects too.
Yeah. Are you going to show some of the projects today?
I think some of the projects that we've worked on are being shown today, so I think that will be exciting to share too. Yeah.
Yeah. So if you can share your screen, so maybe we can start a little bit. For those at the start, we ask a question. who knows Grasshopper, who use Karamba 3D in Grasshopper. Some people knew Karamba and use it actually. Some of people, for example, like Melih, use Karamba in the module in the university. So this is interesting that some people are using Karamba and the university. The same on the Politecnica in Milano, in the university there. So actually, it's really fascinating that people are actually using already Karamba 3D at universities. I know that Clemens is coming to Norwegian University, NTNU. Is also
Yes.
going to present. I already heard rumors about that. So I really liking your attitude for sharing really from the start at the universities. Okay, we can see right now your screen. Yeah.
Okay.
So Matthew, the floor is yours. I will going to follow the questions. So yeah. So let's talk about Karamba 3D.
Thank you. So I'll just start. So yes, basically today I'm going to be talking about Karamba3D. It was founded by Clemens around 10 years ago, and basically I've just listed the current team members. We're approximately 7 to 8 people, sort of working half-time to full-time on the sort of development of Karamba at different levels, from, for example, full stack, backend, and also a lot of the actual examples and sort of learning materials that we sort of share on our website. Karamba3D has been developed as a collaboration between Bolo and Grumman, and it started as a research project at the University of Angewandte Kunstwien, the University of Applied Arts, Vienna, approximately 12 years ago, where the initial foundings were sort of implemented. As Chris has already mentioned, my name is Matthew, and I'm a computational designer, also a trainer. My background is in architecture, but I've been in practice at the Office of Bolo and Grumman for nearly 10 years. So what is Karamba3D? So some of you have looked at it, some of you haven't. So basically, Karamba3D allows you to do what we call parametric engineering in the interface of Grasshopper. I mean, as you're aware of, this is the platform for learning Grasshopper. So I'm not going to go too much into Grasshopper, but it allows you to do FEA directly in the interface of Grasshopper, allowing you to quickly analyze and get interactive sort of results on your structures.
Yeah. So basically, you have like your algorithm of calculation, and you can do everything in Grasshopper. So you don't need to have an external finite element analysis. But I remember when I've been using Karamba, it was first time. Maybe it was 5-6 years ago. By this time, it was just only beam elements, but I think it was expanded from this time, right?
Yeah, so you can do beams and shells at the moment, and also you can do trusses and membranes as well in Karamba.
Yeah. Good to see that you are also developing. You saw at the start, you showed the slide with the people who work in Karamba. So how many of you are now in Karamba?
I think we're 7 to 8 people. Yeah, mostly half time. There are a couple who are a bit more, but and mostly based in Vienna. But there are also a couple remotely around the world. Yeah.
Yeah, great.
So a small team. Yeah, but growing. So yeah, just as it's embedded in Grasshopper, allows you to sort of couple your Grasshopper scripts with many other plugins that are also in the environment of Grasshopper. So you can do multi-objective optimization or other sort of form-finding techniques in this interface. Just as a quick teaser on Grasshopper, as you probably already know, how do you create a parametric sort of geometric model? And this is the most important thing that needs to be implemented first. So typically you might create this in the Grasshopper environment, but of course Grasshopper allows you to also make semi-parametric models where you also model in Rhino and reference it into your Grasshopper scripts and then bring it into Karamba, for example. So here's just a couple of sliders that show the interface of how you can interact in a parametric environment with a truss, for example. And then once we have a geometric model, in this case with lines, we can then convert this into a Karamba model. This is basically a sort of setup of beams or shelves. We define the supports and we add loads. And these are the minimum requirements that you need to create or perform an analysis in Karamba. Once you have all these entities, you can assemble them and then you can run an analysis to get the live results and then also extract the results from the analysis.
Mm-hmm.
And of course, like I mentioned, it's possible to then couple this with different optimization techniques. In this case, we're using a single objective optimization in Galapagos to basically optimize for a random truss geometry, but also reduce the maximum displacement of our structure. So these sort of gene pools or sliders basically control the positions of these diagonals, as you can see. And over some time, we are able to find optimal designs for our structures.
So this is example of generative design, right? But
Yes.
but you can connect other solvers, right? You can connect.
Yes, this is just one.
Yeah. You can
the
connect
basic.
Octopus and yeah. Do you have
And
your
so-
favorite? Do you have your favorite one, optimization solver that you're using with Karamba?
I mean,
which one you will recommend to everyone if they're working with some optimization work?
We were using Octopus a lot because it was developed by one of our colleagues, Robert Feelinger, actually. So we were using Octopus a lot in the past, and now we're also looking, for example, at DC from MIT, and also Wallasai as more sort of interactive sort of tools for multi-objective optimization, for example. But there's a lot of different tools, and if you, for example, want to go into machine learning as well, there's a lot of other tools that are available. But currently I would say we still stick to Octopus or Galapagos as the sort of main ones. They're the easiest to use sometimes. But there's a lot of other tools available. And I think it depends on what type of optimization technique you're trying to achieve as well. And I think you can also go into a whole session about optimization as well.
Yeah. Maybe it will be the topic for the next webinar.
Yeah. And basically with the functionality, you can perform different analyses on your model. You can do form finding as well. And so here are just a couple of images from our website that just show some of these different procedures in terms of, for example, optimization, the large deformation for form finding, then analysis in second and first order theory, as well as buckling modes and eigenmodes, which are essential to sort of test and analyze the stability of your structures. Of course, it's very important to display the results. So there are a couple of different components which allow you to do this: the model view, the beam view, and the shell view, which you can display graphically. But of course, you also want to be able to extract numerically all these results, for example, as lists, so that you can match the beam forces, for example, with each individual beam at different positions on that specific beam as well.
So now you are showing all the components which are available from the Karamba3D toolbar, right?
Yes, I think there's maybe a couple missing new ones, but this is the sort of range of different toolbars or different components that are available.
Yeah.
And of course, one of the main sort of drivers in the last few years is the idea of interoperability, and Karamba allows for many interfaces between different platforms. So Grasshopper itself has many methods of how you can import, export geometry itself. For example, run it inside Revit, where you can then take the geometry from Revit, bake it into, or bring it into Grasshopper and create a Karamba model, or vice versa. You can take your Karamba model and bring it into Revit. There's also, we've been developing currently an interface for BOM, which allows you to then export your models into many other SVE basically platforms. And then in the new developments, we're also looking at developing a SAF and a Speckle interface, which will be released with the new version of Karamba as well.
Yeah, like Speckle release, that sounds really interesting. And this actually can open the new realm of the possibilities, right? Because with the Speckle, you can connect to any software. But what are the BOM connection right now? Is it developed already? Have you been testing it with the sub edit tabs?
BOM development has been working, so it is developed for the interface of BOM, but because each software environment has its own way of naming cross sections and the way it generates, for example, loads and beams, there might be, for example, some small bugs in terms of the import into these softwares, but generally the export from Karamba into the BOM interface works quite smoothly.
Hmm.
So it's always this problem with interoperability about matching the data so that it imports in the correct way. But
Mhm.
this is, I think, some of the things that BOM and Speckle are trying to tackle on their side. Yeah.
Yeah. But just one more question, because we have already Karamba and Sophistic has a live link, right? Can these
Uh,
two softwares cannot be connected directly? Do we
I'm
need
not. I'm not
both?
sure there's a
Okay.
Sophistic live link to Chromebook as far as I know, but
Okay.
maybe
Okay.
yeah. As far as I know, at the moment there isn't. At the moment, there's a live link to Robot and RFM Ashtab,
Mm-hmm.
but at the moment, I thought Sophistic's only available for BOM. We ourselves use RFM Ashtab on a
Mm-hmm.
sort of daily basis. That's why sort of our key sort of platform, but there are many options for exporting, importing your geometries into other interfaces as well.
Yeah. Is it the robot connection right now? Is it free to download and test it?
It's included in the
Included. Okay.
native Karamba, yeah.
Oh, okay.
hmm
Great.
So as I mentioned, one of the powers of, for example, Grasshopper is the idea of how we can do optimization, where in sort of early sense using generative design was to look at how evolutionary theory is paired with computational sort of techniques. So in this case, for example, what happens when we start to put an obstacle in this sort of truss design? How can we optimize the truss to reduce the, for example, the maximum displacement, and then create an optimal truss design for this particular design criteria?
Mm-hmm.
So now I'm just going to show a bit about the basic setup for those who've never used Karamba. And in essence, the model that's created in Karamba uses or follows the same principles. Of course, there's much more complexity in terms of how you manage your list and data, but the basic setup is always going to be the same. So first is always that you have to start off with a geometry. So in this case, for example, I'm creating some lines based off some reference points and using a couple of sliders to control the length of these lines. Then we start to bring these and convert them into what we call Karamba entities, so elements. So in this case, we're taking the lines and converting them into a beam element in Karamba. We can specify already, for example, what we call IDs or naming element to these elements. And this is important for example, when you want to retrieve the results for these elements, if you want to visualize the results, or if you want to do a cross-section optimization, for example, it's very, very important to have this element IDs identified. Next, we're able to then set up the cross sections. In this case, for example, I'm referencing a HEA I profile, and I'm referencing the HEA 100 from the library of Karamba. You can also create your own cross sections. At the moment, we only support symmetrical cross sections, so I-beams, rectangular hollow sections, square hollow sections, solid trapezoidal or rectangular, as well as pipe sections.
But can you define by your own custom profiles?
You
For
can't
example,
just
with the JSON or
at the moment you cannot define custom profile shapes, but you
mm-hmm.
can define custom cross-section properties. So, for
Okay.
example, if you have the properties of that specific cross-section, you can actually create your own cross-section with that property for analysis. But this might get complicated. For example, sometimes if you have asymmetric or more unique types of cross sections, and there's a lot of information on the forums for those who are looking at sort of custom cross section shapes too.
Okay. But what about the L profiles? Are you consider them as asymmetric L
No, this is
profiles? No,
asymmetric,
no,
so
so
they're
it's a,
currently not in the
mm,
default library. But of course, like I said, you can define
yes.
yourself these angles or
Yeah.
whatever. Yeah. hmm
Yeah. Great. Thanks.
Um, And of course, it's also important to assign materials to these cross sections. In this case, for example, we're taking standard steel. So we have, for example, the standard steel, concrete, timber materials in Karamba, but of course, you can also create your own materials by giving in the properties in for isotropic or orthotropic materials. Next, we then define the support conditions. So taking points in this case as an input, then we basically define the degrees of freedom. If it's a fix, if it's a roller, or if it's pin, can basically support, and this is then assigned as a support for the model. And lastly, we need to then define the loads. In this case, I've defined, for example, two line loads, uniformly distributed line loads, one on the vertical element in the load case vertical, and one on the horizontal element in the load case horizontal. And we can, for example, in this case, define multiple load cases. And basically, once you've defined all these entities, you have to collect them into one single model. And this is using the assemble model component, as you can see here. Next, once you have the
Just
model.
sorry to interrupt. Can we just come back to that one, because we have a question about like definition of seismic loads. Can you
What's
define
the
that
question?
seismic loads?
Okay, so at the moment, this is something that we're currently working in with the implementation of load combinations. So load combinations are going to be released in the new version, and with that, we're then going to be looking more detail into seismic loads. But currently, for example, you could simulate a seismic load in terms of a horizontal gravity load as a sort of very simple basis. But this is something that we're currently working on for the new version to at some point implement more detailed seismic analysis.
Yeah. We have also a question from David about the profiles and the catalogs. Can you also divide these profiles by the countries? Like different countries are using different standard profiles, or
Yeah, so you
just,
can see, for
yeah.
example, the node has a country input there. So you can select per country.
Maybe you cannot zoom it. Let me see. It's a little bit. Do you have maybe bigger?
You
Yeah.
see it?
Yes. Yeah. Now we can see it. Yeah. Great.
So you can define per country, shape, and family, for example.
Oh, that's great. So this is about cross section. Is it the same with, for example, loads? If you define some standard loads from different countries, or
No,
you work
loads are
with
totally
those?
no. So loads are totally independent. Basically, you can define however you want the loads. So there's no standard way of defining because although most countries probably work very similar in terms of code, each country is somewhat different, and it's very
Yeah.
very hard to for different geometries. It's not sort of always a preset way. So it's we provide more flexibility in terms of defining loads in this case.
Okay. Great. Thanks.
So once you have your model basically assembled, we then run different types of algorithms. In this case, for example, I can analyze it. In this case, I'm analyzing it with all cross-section sizes to be the HEA 300 size, and then we get basically the results for the maximum displacement for each load case. In this case, I have two load cases, so we get two outputs for the results. Alternatively, we could also perform an optimization of the cross sections. So in this case, I'm allowing Karamba to basically give us the cross section sizes for the given basically design or this setup of our model with the loads and the support conditions that have been defined. So picking from the entire HEA catalog of profiles. And this would then give us then also an output in terms of displacements for those load cases. And lastly, once you have analyzed or optimized your model, then you want to, of course, visualize them. So first is to look at the model, where you can, for example, look at the supports. You can look at already how it deforms. You can look at maybe how the model is set up in terms of its loading as well. Next, we can also look at the beam view, extract results in terms of section forces, render out, for example, the displacements, the utilization, for example, of our model. And lastly, if you want to also extract numerical results, you can use the specific components. In this case, I'm using a utilization component to extract utilization according to Eurocode 3 for these three beam members.
Mhm. About visualization, actually, it's a question from Liam. Is there
Mm?
any Karamba tutorial that explaining these topics about display scales, section forces,
Yes, we
render
have
settings?
many. Yeah, we have many free videos on our website that you can go in to learn a bit more about these specific
Mhm.
workflows if you're interested. I'll be also showing later in the live demo
Yeah,
how this
yeah.
works. Yeah. So now just to jump on a couple of case studies to show how Karamba has been used in different projects at different scales as well. So the first one is a project that one of the first ones where we implemented Karamba in a sort of large scale project at the office of Bollinger Grohmann. So this was a competition that the architects, Delegon Meiser Associated Architects won, I think early 2010s. And so they basically designed a sort of a floating roof or in the sky, where on the ground level it would be the exhibition sort of retail center for Hyundai, and in the what we call the programmed roof, there will be other functions such as event spaces, sort of multifunctional halls and offices and stuff like this for the staff and also for the users. So one of the challenges was how can we sort of create a very, very open and expansive space on the ground floor.
Mhm.
So one of the main tasks for us at Women was to work out how can we minimize the impact of the columns on the ground floor. So what was in a way fixed were the core positions. Basically, these were important for the overall vertical circulation, but also for the global stability of the entire structure. And then in terms of the column positions, we were quite flexible. So rather than having a standard grid, which would actually render the entire space unusable for the sort of the car exhibition, we opted for an option where to cluster columns in, for example, groups
Mhm.
that in itself would also get more stability in lateral stability, but also allow us to have a bit more flexibility in the plan of the structure.
So
So
the red rectangles are
the
actually
cores,
the cores,
yeah,
and here like the piles, kind of columns. They are in the groups, right?
yeah, they're the column groups
Mhm.
that were then sort of optimized for. So in this case, the architects gave us a footprint of where columns could potentially go,
Mhm.
depending on where they had placed program. And then we set up, for example, a multi-objective optimization to look at three different primary objectives. One was to look at reducing the total mass of the roof. One was to reduce the number of clusters, but also
Mhm.
looking at the number of clusters in total. Uh, and also the other one was to remove or reduce the displacement. And often when we're looking at multi-objective optimization, the in a way the case is that often we have in a way different objectives which are contradictory to each other. So often, for example, when you want to reduce the displacement, you often have to increase the mass. And this might then also increase the number of clusters of columns. But of course, we want to maybe reduce the number of clusters so that we
Mhm.
reduce the cost and the mass of the structure. So often these are not really all in alignment. So we have to then study what we call the pre to front of the results of the analysis. So evaluating which trade-offs we're willing to basically work with after we have performed the optimization process.
Mhm.
So basically, after this optimization process, we came up with this scheme, which together with the architects, which basically was then optimized totally in Karamba. So here you can see a image of the entire structure. So at some points it becomes like a totally spatial framework where we have full ceiling height trusses, and at some points it becomes sort of more just small, lightweight single roof structure. And we have different orientations in the roof structure and the sort of trusses that sort of create these programmed roof. And so it was a very, very complex exercise to in a way do it manually. So that's why it's very, very key to set up in a parametric way that allowed us to control the position of the columns, but also how that then dictated the layout of our trusses. Here you can see
It
image.
was sorry for interrupting. It was the
Yes.
question about the optimization. Have you used the penalty function for optimization?
Oh, this I can't
No.
remember anymore. This,
Okay.
this
Okay.
is, I think there probably was, because this is something often you might want to, right? So have a hard no yes that allows you to sometimes make the process quicker. But I can't remember if this was implemented. Maybe there was a case that allowed us to check if the column was inside or outside a specific boundary condition, but I'm not 100% sure anymore which
Okay.
the exact optimization procedure. So here is then just an image of the entire roof, showing also the volumes of the core, and also this sort of office tower that sits at the back, and how these sort of shaped sky fits in with the core structures. And then a quick image of the structure, the roof structure under construction. As you can see, it follows a very, very similar principle to what we designed in the sort of early sort of concept and design development stages of the project. And I think it was quite successful too. The next project was a small project that the engineers and architects of Nikon Sekai developed. So they developed this also approximately, I think, 10 years ago, 2012, 2013, to basically create a optimization to design the shear wall of this sort of office building. So as we all know, Japan has prone to seismic activity, so they developed a quick script to basically analyze the performance of the shear wall, coupled it with Karamba to look at the actual opening sizes and where they could then optimize the position, but also the sizing of these. So they had a script that allowed them to set the width, and I think also the height, which then was directly coupled with Karamba, which allowed them to analyze and interpret how this shear wall was behaving. Here you can see a model in 3D of the structural model that they created in Karamba that they used to analyze. And then I think then of course they brought it into their own software where they would then do further analysis for the design, for the development of the structure, as well as for execution of the structure as well. So Karamba is often used as a sort of tool in the early design phases, where you can really study how different changes or different sort of design ideas might influence the entire structural behavior of your buildings.
So actually, this case study that you showed actually is the answer for one question. Does it work for meshes or maybe only for frame elements? It was about
no, this is also
Karamba,
meshes.
yeah.
Yes, this is a mesh, basically like a wall element here.
Correct. Yeah.
And the last project that I wanted to show was a fun little project that we did with the Technical University of Graz, engineered by Bolo Groman. It started off as a university project with the master's students of architecture. And the client basically came to the university and said they wanted to develop these pavilions where they could showcase the local sort of timber industry, but also showcase the different hiking routes in the area of this alpine region in Austria. So the main idea behind this pavilion was to sort of have these twisted, sort of very, very thin lamellas, which start to basically create structural stability due to its twisting angle. So we did some early initial studies, for example, on site, where by twisting these lamellas, and often, for example, if you just have a flat one or vertical one and you just put a load on top, it tends to buckle very easily. But by twisting it at approximately 30 degrees, which we studied in some Karamba models, we are able to see that we're able to basically increase the buckling length of our element itself, so basically increase the stability. So this was forming the main structural sort of typology of this pavilion. So
do you know some of the numbers for how much you can increase the length of the backlink length?
So I think this was basically the what we sort of, you see the graph here. I mean, we didn't do fully entirely scientific results. It was a very sort of quick process where we just to try to understand how these might work in terms of its structural behavior, because it wasn't a sort of research into the actual specifics of the twisting behavior, but on a very, very sort of high level, just to understand a little bit how the twisting would influence this. And I think there's a lot of research that we hope we can further develop from this project in terms of really studying this in more detail, how these twisting angles could really be influential for creating structures similar to this. But we just did a very early sort of Karamba study and physical study just to sort of anticipate the behavior. And then with this, this was then brought into sort of the design of 3 different typologies, each, for example, that fits in a different sort of location and site restraint. But the entire sort of typology of these, each of them are the same, where we have these twisted sort of timber slats. They're 14 millimeters thick, so really, really thin, and approximately 3 meters in height. Then there's CLT sort of panels on the top and the bottom, which are CNC'd, and basically these panels or these sort of lamellas are slotted in from the top and then slotted also down at the bottom in this sort of base plate. There's a concrete, what we call base, where these elements are then fixed to, and everything was prefabricated offsite and brought in either 1 or 2 pieces on to the site.
And speaking about the concrete, we have some questions from Anders. Is this any workflow? Can Karamba be used for reinforcement concrete? For example,
yes, so
placement for rebars or something like that?
Yes, so there's like there's an optimization process for the reinforcement of structure of concrete shells, for example, that you can also look at, and we'll be releasing some more videos on that in the near future, how you can do a bit more detailed optimization of concrete structures. But there is some definitely possible to work also in concrete too.
Yeah, Anders. So you can check out. Definitely, you can find out with Karamba.
So in terms of the process for this project, and often many projects, is that the architects and the students worked with a random model, which was parametric setup in Grasshopper. The information was extracted from the Grasshopper file and brought into Karamba for very first initial structural analysis, just to see how the behavior was set up, and also applying also, for example, all the wind and all the load conditions to it. Then this was then exported into RFM, where we did the detailed code checks and really analyzed in structure and for the structural reports that were needed for the final submission. Yeah. Oh, sorry. I think that was the last stage. Yeah. And I forgot to mention that basically in this case we also added then these vertical walls, which were also there used for the horizontal stability of the entire structure. So they were not only used for sort of showing the sort of local hiking routes, but we also use them as structural elements because they were something that was also required from the client. So we actually managed to also integrate them, and they were important for the entire structural system as well.
Really interesting case study, and actually it was actually 3 of them. Was really interesting. So maybe we can ask people which one you liked most. You showed at the start. You showed at the start optimization of the column, and next one it was about optimization of the wall with the mesh, and the last one was the twist pavilion. So just let us know in the comments which one you liked most. For me, this twist pavilion. It's a really cool, maybe the smallest like in the scale, but actually the idea back, it's really amazing. It's more maybe architecture than the structure analysis here. That's why maybe it's more sexy.
Yeah, and if you want to read up on more about these projects, they're also presented on our website in more detail, so you can have a look and get some more information about these as well.
And great presentation, like great renders and gaze load cases. So yeah, that's yeah. I saw on your website you have like hundreds of examples from the project from the whole world. I'm from actually from as you showed, from Japan, Australia,
Yeah.
to the whole Europe. So that's really cool. Okay, so now you would like to show us what is coming in the Karamba3D 30.
Yes, so just a little teaser on what's coming in the next version. So as I mentioned, load combination is something that we're currently working on. So for example, here, just a quick preview of how to implement load combinations, and also now the possibility basically to analyze structures basically and optimize on load combinations or specific load cases as well. And we'll be hopefully releasing more information about that in the future. The BOM interface, if you're interested to do that, you can also find information on our GitHub page. And also, there's also the possibility, if you're interested, to also use Karamba outside of the environment of Grasshopper in C# or in Python, for example, using Visual Studio or in Python. And you can also find more information on our GitHub page with this link as well.
Yeah, so actually you can even expand it more, right? If you are missing some possibilities, so you can actually access the API and if you know a little bit of C# or Python, is it available in both languages, right?
Yes, so if you just want to do it natively in code, then you can do both languages. But if you're working in Grasshopper itself, it should be, you can also create your own custom components using our API in C#.
Yeah. Mm-hmm.
And yeah, of course, our ongoing development. And if you have any feature requests or bug reports, you can announce them on our GitHub page here, where you can also find the current work in progress version of our version 3.
Mm-hmm.
And that's it for the sort of presentation of Karamba.
Yeah,
And
maybe before you would like
Mhm.
to jump into the Grasshopper, before you will jump, maybe we can answer some of the questions.
Okay.
So let me see. Most people said that they liked most the Twisted Pavilion is the best, and actually that was the question from David. Do the twist elements carry much load? I think the question if they can carry more.
They. I mean, I'm not 100% sure of the exact value in this case. I I haven't looked at the results for a long time. So, but yes, they were definitely carrying the load. So they were also crucial for the vertical load takedown of the structure, whereas the horizontal stability was mainly achieved from these vertical panels. They contributed for the vertical load takedown.
What about Eurocodes checks? Do you have it in Karamba?
So currently, when you do, for example, so in the current process of Karamba, it's written for, if you look at utilization, for example, you can do Eurocode checks for steel, so Eurocode 3. Of course, if you want to look at timber, there's this plugin called Beaver, which allows you to do Eurocode 5. And we're also currently looking into developing a more concrete-based analysis when you're looking into Eurocode 4. But of course, you can extract the results for every single element in terms of forces, the actual node of each part of the element, and you can then do your own calculations for Eurocode or even specific other norms that you might work with. So you can actually extract and reinterpolate the results for other Eurocodes or other norms that you're working with.
Yeah, because it was also a question about the standards like BS or Indian, so it can also be defined, right?
I mean, in terms of standard, we don't have a sort of standard calculation at the moment.
Yeah.
It's sort of, you can read more about on the website in terms of the background of the calculation, but you can basically At the moment, a lot of it's written for Eurocode
Yeah.
free, but of course, it doesn't mean that you're restricted to only Eurocode free. It just means that some of the results, some components, for example, the optimization or utilization check is done for Eurocode free, but hopefully, in the future we're going to be implementing these for other Eurocodes as well.
Mm-hmm. What about components like from Lunchbox? It was a question from Anush. Lunchbox has the creation of 2D trusses. Like you can really easy create 2D truss. Can it be used for creating Karamba models?
Yeah, definitely. I mean, that they those components basically just create the geometry for you, and you can then sort them into different typologies for your structure, and of course, create a Karma model for this very easily. Yeah.
Mm-hmm. Have you tried, Matthew, to connect Karamba with some of machine learning components?
I mean, we have been doing a little bit of research, but not like directly. Basically, what we've been doing is try to do iterative design where you, for example, analyze, for example, a building with a variable span, and then you save all the results, and then you try to give the results to, for example, a machine learning algorithm to then help you to predict values. So that's what we've tried to have a look in the study into, and we're also going to be showing this at a workshop at AAG, focusing a little bit more on carbon analysis and how we can maybe predict the carbon footprint of buildings using the results of Karamba. But it's more on a very, very sort of theoretical level still, right? And I think a lot of these studies are so, but definitely possible. Yeah.
Can we assign diaphragms for floors in Karamba3D?
At the moment, it's only, I mean, you can change the materials, but basically, it's always going to be either a shell or a mesh, shell or a membrane for mesh or sort of surface geometry, and for beams, it's going to be either basically bending stiff beams or truss elements that we can currently define.
Yeah. And it was Fenji, question from Fenji about definition of materials. You already mentioned that, Matthew, but what about anti-isotropic materials? You can define it as a custom material or not?
That's not possible for anti-isotropic materials. It's only for iso and orthotropic materials. Yeah.
Yeah. Okay, we have more questions, but you, Matthew, have you maybe you can present some of the.
I'll just show the live examples.
Yeah, some go live, so we can maybe test it.
So
let
you
me
can all
see.
see
I
my
will
screen
check
now?
it. Yes, we can see it right now. Maybe I can make it a little bit bigger.
Okay, so this is just an example. I think Chris will also be sharing this, but you can also find it on our website where you can create a simple portal frame, right? So here we just have created some elements. Basically, the width of our frame can be controlled by this slider, and the height can be controlled by this slider. At the moment, then they're brought into one list where I basically label each element with A, B, and C. We're defining a cross section in a way for all of the elements, and in this case, all of these elements are having the cross section HEA 300. Of course, if we wanted to, we can change the cross section by selecting and changing a name here, or if you want to change the family, for example, you can also do that by selecting a different family. Someone asked about the countries. You can also select from a different country range, or you can also select a different shape, for example, and use that for the to assign your cross sections. In this case, we're taking the entire library, in this case 24, and I'm selecting one of these as my cross section for the initial analysis, because this is what's important when you do an optimization. You need a starting cross section. So I want to compare the results of the starting optimization with the analysis where I selected HEA 300. Here we're able to assign materials. So here you can also select from different types of materials, for example, from the list, family, and the grades of those materials as well. And so there's grades for many different countries as well found here. Next, as I mentioned, it's important to define the supports. So if I was to now turn on this, you can see our supports are defined at basically the bottoms of our frame there. One of our supports has the Z in the rotational axis released, and then the other one is basically released in the RX, rotation the X, and RZ. But by clicking or on these, you can then deactivate or activate specific constraints in your rotation, and you can see that updating live in our model there. For our loads, I've created 2 load cases, one for vertical, applying a 5 kilonewton per meter as a line load on the entire element. In this case, it's local to the element. So in this case, we have to know which is our Z direction of our element, so that we apply a force of 5 kilonewtons per meter in the Z direction of the beam. If we set the global, it would automatically be set so that the force, in this case, I have uh, in this case, you'll see it like here, that if I change it to global or local, the orientation of our load will change because the direction of X is different when we set it to global or local to the element.
If you can just come back to the support, we have
Yes?
2 questions. Can we define the stiffness?
No, at the moment, if you want to define stiffness, then you can add a spring, for example, or like a spring element between your elements to your support to define a specific stiffness as a support.
Yeah, so actually you answered 2 questions because the
Yeah.
second was what about the springs. So yeah, so
Okay,
this is
yeah. There's examples on our website or on in the installer that comes with Karamba that helps you to understand a little bit about how you can do springs, for example. Lastly, I just wanted to show how we use the beam joint agent to then define, for example, joints between elements. So in this case, for example, I have I'm releasing the Y in the rotation of the connection between A and B. And I can also release, for example, TY, TX, or TZ in a specific direction at another joint as well if I wanted to. So those are how we can work with joints. All these information is collected in the assemble model, and this is what we need to then run any analysis or optimizations of our model. So the first step is what we're doing is then we're running the analysis of the model. So this is analyzing it with the HEA profiles or HEA 300 profiles. So we get displacements for each load case, 0.2 centimeters and 0.05 centimeters for the second load case. And I'm going to talk about the optimization later, but here you can see that the model can be visualized using the model view component. If I open this, we can, for example, look at the deformations of our model by activating the slider. You can look at the reaction forces. For example, you can increase or decrease the slider here. And often this is, for example, very small shown here. You can visualize the loads, which I've already visualized, or you can turn it off or on. In this case, I'm visualizing the horizontal load case, but of course we can have a look at the vertical load case too, which is like this, of course. And here I can also turn on my local axis of the beam if I want to see where my local axis, and now I have to actually go into 3D to actually see this because the local axis are shown in 3D where we have, let me just hide also the beam view first so we see the elements. The local axis refers to the X direction of the beam, which is always in the axis of the beam, the Y, which is the green, and then the Z, which is the blue. A quick sort of tip is to remember RGB, X, Y, Z. So green, that's a red,
that's smart.
blue,
That's smart.
a red, green, blue. Yeah, so RGB. And then if I turn on my beam view, there's also opportunities. For example, sorry, I looked at the tags. So you can also look at the element tags, which show you the list of these elements in numerical order. We can look at the element IDs, for example, A, B, C. We can look at the cross-section names. They were all assigned HA300s. We can look at the material names and
Can we
also
change
the
can we
load.
change the scale of the text? It's that it will be bigger or
You can change it in the ini settings,
is that
for
yeah.
example, at the and there's a video on that if you wanted to look
Mm-hmm.
into changing the scale. Of course, in this case, I have a very high resolution screen, so it's showing the numbers often
Right.
a bit smaller. Yeah, so then we can look, for example, into the beam view. And for example, if we want to look at the normal forces, you can turn on the normal forces and also render the meshes with the numerical values of our normal forces. So here you can see, in this case, we have compression in both our vertical elements in the vertical load case, and then horizontal, we have, in this case, compression in the top beam. We can also
Mm-hmm.
look at the if we have bending moments, where these might be, and if we then go in now, uh, remove the release, then you can see that it becomes basically a moment frame as well. So moments are also then carried between the uh, different frame elements too. So you can really see how the structural system changes as we release or add joints to our system. And what I wanted to show lastly is this optimization procedure where we take this model, we take the starting cross section, and we apply a list of different cross sections for Karamba to choose from.
Mm-hmm.
When we do so, the optimization process has given us a larger displacement. In this case, it's actually optimized for smaller cross sections because this actually fulfills the 100% utilization that we need to achieve, but the displacement is higher with a smaller cross section in this case. But because the main objective is to optimize for utilization, but
Mm-hmm.
we're also able to optimize for displacement. If you put in a numerical number, for example, if you put in 2, then it will optimize for maximum 2 centimeters for all load cases. In the future release, we're going to have the opportunity for you to optimize displacements and utilizations for specific load cases or load combinations as well.
And this is in my opinion, like this is the biggest superpower of Karamba over like another software that you can calculate that what you showed that you can
Mhm.
make your forces, and actually this is kind of every single structure analysis software can do, but this optimization, this is pure gold.
Mm. Yeah, so this is one of our main tools that I would say a lot of people like to use in this to basically give us a very, very quick sort of idea of how the cross sections should be sort of in a way pre-designed for a
Mhm.
specific scenario. I'll just jump onto the last example quickly, which is a much more complicated one, but just to show, for example, a more sort of
Yeah.
structured way of how you create a setup. In this case, I'm creating a bridge, a footbridge here, which is located in Vienna. It's basically designed by the office of Otto Wagner. And basically, in this case, what we're doing is actually taking a simple line and running a simple analysis of this line by using, for example, supports at both ends. One is a sort of roller, and the other one is a pin support, and simply applying gravity. And then we're extracting the deformed shape, which is this one here, and using that as the actual geometry for the bridge arch. So then just using some exercises in or some components in Grasshopper, we're then reversing it and moving it so that we are able to create this inverted sort of hanging shape that was resulting
Mm-hmm.
from the deformed beam. And then we start to use these to add the verticals and the horizontal sort of struts for the bridge design, which you can go through a bit more detail on how this is set up. I'm not going to talk about the geometric
Mm-hmm.
setup of this. But basically, what is then done is we collect all of those elements into one list with multiple branches. And this is one of the most powerful things of Grasshopper and how data is arranged in Grasshopper as well as in Karamba. So here, for example, we can use one component to contain all of our elements, but have levels of control of all these separate elements as well. So in this case, I have 5 different typologies identified in one list, but by using different branch structures or data structures, we can control, for example, the naming and typology of each of our branches. For example, horizontal, arch, hanger, cross girder, diagonal, by grafting the inputs so each of your
Mm-hmm.
path structures match. And then the same follows with cross sections as well as materials. So cross sections, we here have defined 5 different types of cross sections, 4 of them eye profiles, and 1 of them circular profiles. And these are all unique ones that we defined ourselves. And we've assigned them to also uh, in a single list, which we've also grafted for each individual branch.
Mm-hmm.
With this, we're also able to convert these elements into trusses or beams by setting bending off and on by using this same typology by using true or false. And then in this case, we're also using the orientate element to basically rotate the specific elements in our structure. In this case, these vertical hangers. I'm using this here to define our support conditions. So having a roller support and then a pin support at one direct and other side. And then for our loads, we have gravity in one load case, and we have in the second load case a sort of line load uh, on these beams there.
So
On
Karamba,
in beams.
so Karamba is not just about buildings; it's about also bridges, right?
Yes, so
Mm-hmm.
you can do buildings, you can do bridges. Also, some people are looking into, for example, furniture design, industrial design,
Mm.
and more sort of smaller objects as well. So there's multiple scales at which you can look and use Crumba. So all of this is then brought into this assemble model. Once again, we get information about the total mass of our structure, and we run the analysis and get the results of
Mm-hmm.
the analysis. In this case, maybe you're interested to know how the buckling of this works. And so
Mm-hmm.
here, in this case, I have the first buckling mode of this bridge, and I can visualize the first buckling mode by turning on the deformation. And so we can also add more buckling modes for the analysis, and we can also visualize the different buckling modes and see how the structure might buckle at some point as well. If it's local or if it's global, if you have local buckling issues, for example, in a specific column or in a specific beam, it's quite easy to see where this might happen with this component as well.
Mm.
So that was a quick sort of preview
Yeah.
into Karamba, and I think these examples I think will be quite fun for everyone to sort of play around with themselves. And I think I just would like to, if there's a couple more minutes for questions and stuff, I'll be
Mm-hmm.
glad to answer these.
Yeah, thank you very much. It was amazing, and I have confirmation from the audience as well. David and Habab just wrote the comments that this is amazing, and they will give a try to Karamba. So that's great. We still have a few questions. We are out of time already. It's 3 p.m. But yes, sure, we will answer all last questions. Uh, yeah, this all the files that Matthew showed us in the Grasshopper. We are going to share if you register your email on Learn Grasshopper, so you will get them together with the PDF from the presentation, so we can go through all the case studies. A question from Liam: Is there a rule in proportion of colors, 40% red and 60% blue, to decide how well structure is optimized?
The blue and the red actually accounts for, in this case, basically compression and tension in your
Mm-hmm.
beams. So it's not, in this case, it's not really showing you uh, if it's actually 100% utilized or not. Often, for example, we probably want to, in this case, when we're looking at load combinations, most norms dictate for example, safety factor of 30% often. And so when
Mm-hmm.
you're doing sort of optimization without considering load combinations, it's maybe good to have structure optimized for 65, 70% utilization so that you'll be sure that your structures are not going to fail when you apply all the safety factors onto it.
Mm-hmm.
So, of course, it's also making sure that the structure doesn't fail, but you also don't want to make sure that your structures are very underutilized. So, for example, if all of your structures are only 10%, or all of your elements are only 10% utilized, you also may be over designing
Mm.
the elements as well. So, it's also making sure to check the range of results that you might get in the utilization values. But yeah.
What about P delta effects?
What
I'm
is
not
P
sure.
delta's effects? I'm not too sure what that is.
Yeah, I'm not either. Okay, let me see. There's war. What are the difference between different analysis algorithms?
So at the moment, you can do analysis in first order, second order theory. Then there's also non-linear analysis. So basically, there are difference of rules that apply or different calculation methods for each type of analysis. For example, that are important for different stages of a project, and depending on the structure models that you are basically working on, you can read up a bit more about the theory. This is standard procedures or analysis in standard FE calculation when you're looking into analysis. So there's a lot of theory about this too.
Okay, and the last question, I think Manuel asked about if we can use Karamba for the product based on the lattice structures.
Yes, you should be. In terms of lattice, do you mean like a sort of grid or like a three-dimensional space frame, I'm assuming? And I guess if so, it definitely is possible. And that's often a case study that people would use.
Yeah. Thanks, Adol, once again for accepting this invitation and for this amazing webinar. People were actually happy with that showcases that you showed, Leon. Thanks, Matt. Thanks, Chris.
One last thing. For
sure.
those of you who want to actually get a demo license, you can also request for one on our website. I forgot to mention this, so you can test out the full features with more with more elements for a 1 month period to really work out and test all these options. Yeah.
Yeah, that's actually amazing. So yeah, if you will be interested, we already talked with Matthew that if it will be for people interested in the training on the Learn Grasshopper educational platform about using Karamba. So we talked with Matthew that we can do it together, but actually it depends on you if you will be interested. So reach me or Matthew. You can just write me on the LinkedIn on the chris@learngrasshopper.com if you are interested. So maybe we can do it together and just make it. And just last thing, if you are interested in the new webinar, so in 2 weeks, I have a webinar about C#. So Matthew just mentioned that you can also write your own components in the C# and access the Karamba API. So maybe will be possibility. I'm going to have as a guest Marcin. Actually, Clemens was the supervisor of Marcin PhD studies, so they know each other quite good. And Clemens is going to visit him in Norway. So Marcin is going to tell us in 2 weeks about how we can actually apply C# and how we can actually use it in the AEC industry. So yeah, for sure he's going to mention Karamba there. So everyone, if you are interested, you can reserve your seat. learngrasshopper.com/webinar C#. So thank you very much. Lots of congratulations on the comments for you, Matthew. So thanks you again, and I hope we can make another webinar, maybe another little bit more about optimization, about generative design.
Yeah, we'll see what interests there are from the people. Yeah, I think definitely send in some suggestions also on what you would like to see.
Okay. Thank you again for being with us, and yeah, let's stay in touch. Bye.
Thank you.